Hi, in this video I will outline my project on the effect of demonstrations for deep reinforcement learning-based control of concentric tube robots. Concentric tube robots, or CTRs, consist of pre-curved superelastic tubes that are concentrically aligned. Their behavior is highly nonlinear, which can be seen in this video. The complex interactions between tubes are also seen from the plots on the top right of the poster, where the effects of rotating single tubes for a 3-tube CTR is shown. Because of the many nonlinear effects and the complex interactions between tubes, accurate modeling of the behavior of CTRs have proven to be difficult. Fortunately, learning-based data-driven models have shown promises for control of CTRs. However, using conventional supervised learning for robot control is suboptimal since the data is not IID but highly dependent on previous states. This is especially the case for CTRs, and research has shown that subtle changes, such as rotation direction, greatly affects the output. Deep reinforcement learning has the potential of bypassing the challenge with data not being IID by maximizing a long-term reward. Still, as robots cannot move faster than their physical capabilities, time is a premium and algorithms need to lend themselves to fast inference. To test different algorithms, a simulation environment is needed. In this project, the developed simulation environment follows the OpenAI GIM interface. The flow of the environment is shown to the mid-right of the poster, where it is seen that an agent can interact with an environment through actions and receives observations and rewards based on these actions. Ultimately, the agent tries to maximize the rewards. In the developed environment, sparse rewards are given after each step. After developing the environment, the effect of demonstrations was explored. This was done by training 2 agents using DDPG and HER with and without demonstrations. DDPG and HER was chosen because this previously has shown promises for similar environments. The agents were trained using 19 CPUs on Stanford's Sherlock cluster and synchronized by MPI. The success rate of the models is shown in the bottom right of the poster. We can clearly see the effect of demonstrations on the initialization of the agents, where the model that takes advantage of demonstrations starts with a success rate around 50%. DDPG and HER without demonstrations catches up after 50 epochs, which corresponds to more than 14 million steps. If one step took 20 milliseconds, this would be more than 3 days of continuous operation and would obviously be costly in our real-world application. However, we see that the agent without demonstrations converges to a higher success rate. This is assumed to be caused by a change in hyperparameters between the models, but it can also be caused by demonstrations biasing the model towards specific strategies. Also, the success rate of both models is assumed to be suffering from suboptimal goal generation in the simulation environment, as the current implementation can generate unsolvable goals.